Once around white dwarfs, these tiny but very, very hot and very interesting little stars. And the first discovery of a white dwarf star was by that man, Sir William Herschel, back in 1783 on the 31st of January. He was observing the star 40 Eridani, and he noticed that there was a small faint companion next to it, 40 Eridani b. Now, we now know that it's part of a triple star system, and I've got a whole video called Once Around 40 Eridani, if you want to go and check out all about that and the planets around it. 40 Eridani, very interesting. It turns up in a couple of different science fiction books, and it was the supposed home in Star Trek of the planet Vulcan and Mr. Spock. So an interesting little system. The second example I have for you is Van Manen's star. This was the first white dwarf star to be found as a solitary star on its own. It was tracked down by Adrian Van Manen in 1917. He noticed while observing another nearby star that Van Manen's star seemed to be moving very rapidly year on year with a high proper motion. And that's always a sign that the star is quite nearby. And so other people then followed up and worked out from parallax that it was 14 light years away. Now, the second white dwarf to be discovered, and our third example here, was another companion star. And this is Sirius B. In 1862, Alvin Clark at the Dearborn Observatory in Chicago was testing the brand new 18.5-inch refractor, the largest scope in the world, and he spotted a faint companion next to Sirius at magnitude 8.4. Now, he wasn't sure if it was a true companion or just a line of sight thing because it was so faint. It might just be luckily lined up. But that white color also indicates a very high temperature, basically a white hot star. And a white hot star would normally be a very bright star, and therefore, if it was dim, then probably it wasn't a companion of Sirius, it was much further away. And there was also something weird about the spectrum, which we shall see in a minute. But 20 years earlier, and quite widely known at the time, was the fact that Friedrich Bessel in 1844 had been studying the motion of Sirius across the sky, and he noted that he thought he had observed a 50-year wobble in the trajectory that Sirius was taking against the background of stars, and postulated that there was an unseen companion, possibly a large planet or something, pulling on Sirius in a 50-year long orbit. Now that's an interesting case, because actually, if you know the orbits of two objects, then Kepler's laws can tell you their masses. So indeed, he was right. There are a pair of stars, as Alvin Clark discovered, in this 50-year orbit. And from the Kepler's third law, you can calculate the masses. You get 2.1 for the bright star and just under 1, 0.98, for the small faint companion. Now that's tricky, because now that we know that they really are in orbit around each other, you have this very hot, white hot but dim star with a strange spectrum that seems to have the mass of the sun, and an ordinary star with the mass of the sun would be much brighter. It would be about 500 times brighter than the level that was observed. So the only way that can be in physics, if you have a high temperature object, it will glow and give off light. So if we see it being white hot, it should be very bright, unless it is tiny. If the surface area of the object is much, much smaller, then that can account for the dimness. But these numbers just didn't seem to stack up, because what it implied was that you had a star that was white hot and the size of the Earth, but the mass of the sun. And in fact, you can do a little bit of maths with that. The sun is 100 times 100 times 100 in volume. It's 100 times the radius, so 100 cubed is 1,000,000 times the volume. But it's a little bit less dense. It's mostly made of hydrogen and helium, so the density works out that it's 333,000 times the mass. Now, the density of the Earth is 5.5 grams for every cubic centimetre, so you multiply those two together and you find that the density of Sirius B must be just under 2 million grams per cubic centimetre, so a sugar cube would weigh 2 tons. That's quite astonishing. But it explains the spectrum, because for such a dense object, the surface gravity would be enormous, and you can calculate that things would have to lose a lot of energy in getting away, climbing out of the gravity well, and that includes light. Light would lose energy escaping from the surface, and it would shift the light from the high energy blue end to the low energy red end of the spectrum. And that's precisely what was being seen in the spectrum of Sirius B. The dark absorption lines in the spectrum of the light, where different elements are taking a bite out of the different colors at very specific wavelengths, were all being shifted to the red end by an equal amount, corresponding to this loss of gravitational energy as the light climbs away from this deep gravity well. Now, that actually turns out to be very useful, because now we have another way of working out the mass of a white dwarf star. We don't have to do it from observing the orbit around in a binary pair. And so for a solitary star like Van Manen's star, you can look at the gravitational redshift in the spectrum and infer the mass. You have to be a little careful, just in case the star is moving rapidly towards you or away from you, which may also cause a redshift, but generally a smaller one. Now, if you're interested, I've got another video that talks all about Sirius and Sirius B, but let's move on to the main topic here, which is what's going on. Why don't white dwarf stars just collapse? They are the end stage of sun-like stars that have come to the point where they've run out of fuel, they've exhausted their ability to carry out nuclear fusion in the core, and the consequence of that is that the outer layers were burned through, converting hydrogen to helium in a shell that eventually drives away all of the outer layers in what's called a planetary nebula. So the star swelled up to a red giant and then puffed off its outer layers, leaving just the dead nuclear core behind as this collapsed, dense white dwarf. And they're super hot because they were the core of a star, but they're not releasing any more nuclear energy. They're not carrying out fusion. It's just the residual heat that is being dissipated, and they will cool eventually over billions of years to fade away and become black dwarfs. But normally in a star, it is the release of nuclear energy in the core that stops them collapsing and that enables them to resist the pressure of gravity. So what's going on here? Why don't these stars collapse? Well, it's all down to electrons in boxes. Electrons are antisocial beasts. They're called fermions. They have half integer spin, if you want to be technical about it. And you can't put two electrons with the same quantum state, the same conditions in the same piece of space. You have to spread them out. You can either spread them out physically in space, or you can spread out their energy condition and keep them apart that way. So what I've got here is some electrons in the bottom row, the lowest energy state of my star, and space is going crossways across the bottom. And if I squeeze with gravity and reduce the amount of space that's available, then I have to stack the electrons up into higher and higher energy levels to keep them apart. This is the Pauli exclusion principle of quantum mechanics at work. And the result of this is that you need to consume energy to push them further and further into these higher energy states. Higher energy means more kinetic energy, means more velocity. They're moving around faster. Their energy is essentially a half mv squared. So the mass stays the same, but as you increase the energy, the velocity goes up. And so in any given instant of time, they will move over a wider volume due to that higher speed. And so they actually, the more you push them to higher energies, the more space they tend to take up. And so this becomes a problem. And the result is a back pressure pushing back out, resisting the collapse. If gravity tried to gain energy by squeezing, it would have to force the electrons into even higher energy states. And so you end up in a balance between those two opposing tendencies. And that's really what causes this new equilibrium and the star to come to a particular size and not just carrying on collapsing down into a black hole. Now, many stars are born in binary systems, and the sun is quite unusual in being on its own. And if you had a pair of sun-like stars born many billions of years ago, then you could be in the situation where the more massive of the partners evolved to become a red giant and then collapse to a white dwarf. And then playing catch up, the lesser partner will eventually swell up at the end of its life cycle and become a red giant as well. And when that happens, if the two are orbiting close to each other, then the red giant star doesn't have a very strong grip on its outer atmosphere, its envelope. But the powerful gravity of the white dwarf next door can actually start to rip material away and drag a bridge of gas across from the outer layers of the red dwarf to spiral onto the white dwarf star, gradually increasing its mass. But there's a limit to what can be tolerated. If you exceed 1.44 solar masses, then the star blows up as a type 1a supernova. This is called the Chandrasekhar limit after this chap here. And Chandrasekhar was on a boat coming from India to study in Cambridge when he worked out all of the mathematics using Einstein's formulae for the energy states of those electrons in the white dwarf stars. The problem is that as you try to force them into higher and higher energy states, you eventually run into the problem that they can't move faster than the speed of light. And so there's an upper bound for how much energy you can push into them, and therefore an upper bound for the amount of gravity that can be resisted by this electron back pressure. And so if you put just one more teaspoonful of mass onto the star, the electrons cannot prevent the further collapse. Electron pressure is exceeded and the star starts collapsing down. And when it does so, of course, this is a very violent process. It triggers off an enormous explosion and the material is completely destroyed. And so your type 1a supernova can be one of the most powerful types of stellar explosion. Here's an example of one, the bright object at the bottom left. That is a type 1a supernova exploding in the outer reaches of its parent galaxy, and it's putting out about the same amount of light when it does so as all the other stars put together. But because these things always detonate at 1.44 solar masses, the idea is that they are very much usable as a standard candle. If you have a known power source and you move it twice as far away, it will look a quarter as bright. 3 times as far away, it'll look a ninth as bright. And so if you know that this thing is a standard power, you can look at how bright it appears and calculate the distance. And so type 1a supernovae can be used as these standard candles. If you see one blow up in a distant galaxy, and you look to see how bright it appears from Earth, then you can work out how far away it must have been. And this makes an excellent way of measuring the distances to very distant galaxies, because these things can be seen at those great distances because they're so bright. And you can recognize that they are a type 1a supernova because they have these clearly identifiable light curves with a very standard shape that allows you to work out exactly that this was a 1a supernova and how bright it was. And it was by doing this work that the Nobel Prize was awarded for discovery of dark energy. The dark energy is the subject of another one of my talks, but it is the outward anti-gravity pressure that is driving the acceleration of the expansion of space. And it was discovered because of the use of these type 1a supernovae that were able to be spotted in distant galaxies and give us a very good way of estimating the expansion history of the universe, how fast it had been expanding at different times. And the shocking result was that it seemed to be getting faster in the modern universe rather than slowing down. But if you're interested, there is another story all about that. And that's all well and good, but then we discovered a number of rather interesting supernovae. There's the light curve here from SN 2009 DC, where it's plotted, and it was really not a very good fit to the light curve of standard supernovae. And it seemed that there was something strange about this one. It seemed there was a certain amount of nickel present and some iron in the spectrum, and that's not quite right. We don't usually see that in these things in the same way as if they had a very large nickel iron core. That's more characteristic of a type 2. So there's something very weird going on. But the fundamental problem is it was too bright. It's called a super Chandrasekhar event. The first one of these was spotted in 2003 and was called the Champagne supernova because it seemed to break the limit. And possibly there are explanations for that relating to just how fast it was rotating and other factors. But a number of them has been seen. This one here that we have the oddball report for, 2006 GZ, 2007 IF. These were also super Chandrasekhar events, and they seem to be as powerful as if they were up to 2.4, even up to 2.8 solar masses of material detonating. Well, that's roughly double the Chandrasekhar limit, and it suggests that it was the result of a pair of binary stars colliding. So that probably explains things. Two white dwarfs forming in a system and spiraling into each other would detonate. They would suddenly exceed the Chandrasekhar limit, and by up to a factor of 2. So this all looks like it's been explained, but it does mean you have to be a little bit careful looking at the spectra of and the light curves of type 1a supernovae and using them as standard candles. And there's one other rather curious feature, and that is that in this standard idea of the accretion binary model, where one star is eating its companion through an accretion disk from a red dwarf, as we've already looked at, the material that was spiraling into the accretion disk would get heated up to high temperature and emit a lot of X-rays in the process. And so if you have a rough idea of how many of these events are going on in a large galaxy, you could add up the total amount of X-rays. And studies of elliptical galaxies looking at the X-ray emissions find there is only enough to account for 5% of the type 1a supernovae. So it implies that 95% of the supernovae are actually results of some other process, and they're probably collisions And there could be many, many of them that are in fact super Chandrasekhar events. So it could mean that we've been getting this wrong, and that their use as standard candles needs to be looked at again. And so I'll wrap up there. Thank you very much for listening. I hope you enjoyed that. Do go and check out a couple of the other videos. If you've liked this one, there's one called Quark Stars and Strange Matter that's had a lot of views and is very popular. So you probably love that one. Thanks a lot. Bye now.